entirely new topic to start today, which is called integration. Okay, and as with most things in maths, okay, we have a process to do one thing. There's generally a process to do the opposite. So we've already looked at differentiation. Integration is basically the opposite of that. Okay, so in the same way, subtracting is the opposite. Yeah, okay, you get all that. So differentiation basically takes us one way, allows us to do one thing. Integration basically takes us back the way. Okay. So it's going to be useful later on. It's going to be used in a context later on, as with differentiation. We've not finished differentiation at all. We need to put it into more of a context. We'll do that in the last unit. The same idea with integration. So we're just going to focus on how to integrate just now. And it helps obviously to look at actually differentiation and working out how to actually integrate. Because obviously if we can differentiate one way, if we can know the answer that we get when we differentiate, then all that integration should do is take us back the way. Okay. So there's three questions here. If you're doing this from home, it might be worth just pausing at this point and differentiating these three, okay? And then see if you can look at a way of going back the way. In other words, a way of finding out how to integrate by yourself. If you can work it out for yourself, then it's all the more easier further down the line, okay? So give these three a bash. As I say, differentiate them. Work out what the derivative would be, and then see if you can work out a formula to get you back the way from what is your answer to these questions, and then just come back to this and see if you're correct, and see the one little thing that you really need to be aware of. Okay, and that's the main reason I want you doing that. I know it seems pointless, and I know it seems much easier to actually just watch the video, but trust me, if you can do this and work this out, what the issue is going to be, then you'll remember it a lot better further down the line. And this is often where people lose marks. From this one tiny little area, people lose a lot of marks in exams. Okay, so give it a try and then come back to this. Okay? Right. If you are differentiating, okay, you've got your differentiation formula. Okay, so when y equals x to the power of n, dy by dx will equal nx to the power of n minus 1. Okay, you multiply by the power and then you drop the power by 1. Okay, so in the first one, you get 15x squared. In the second one, it's minus 5x to the minus 6. And in the last one, you get 14x to the power of 6, and the 3 disappears. Okay, so in terms of looking back the way, if we're trying to integrate, this is our formula. So dy by dx, when dy by dx equals x to the power of n, we can get back to our y, and that will be basically the power, 1 added onto the power, and then divided by that new power. Okay, if you look at the first one, if you add 1 onto the power of 2, okay, that becomes 15x to the power of 3. If you then divide by that 3, you get 5x to the power of 3. If you look at all the other ones, it works too. Minus 5x to the power of minus 5. Okay, increase the minus 6 by 1. Just think about your numbers. 1 more than minus 6 is minus 5, so it becomes minus 5x to the power of minus 5. And then we divide by that new power, divide by minus 5, and the minus 5 disappears, and we're just left with x to the power of minus 5. Right, the main problem comes from this last one. So 14x to the power of 6. If you increase the power by 1, it becomes 14x to the power of 7. Divide by that new power, and you get 2x to the power of 7. But what about this 3? Okay, so the fact that when we differentiate, the 3 or any kind of constant that we have just disappears. When we're integrating, we have to be aware of that. We have to take that into account. In other words, when we're integrating, we have to assume that there could have been a constant in the first place. Okay, and because we don't know it, and it could be plus 3, it could be plus 4, and there's nothing from what we've got in terms of the question, and this is going to be our question, we're going to have to integrate this. There's nothing that tells us that there may have been a constant in the first place. We have to basically take account of the possibility that there could have been a constant, in which case whenever we integrate in a normal context like this, we have to assume that there could have been a constant and write plus c. Okay, so when we differentiate with respect to x, if there is a constant, something without an x, it simply disappears regardless of how big or small that constant was. So anti-differentiation, as it's sometimes known, okay, but more commonly integration, we must take this into account, however, because we have no idea what the constant was, or even if there was one in the first place. The only thing we can do is add on a constant c. Okay, we'll look at this further in terms of calculating exactly. We need to know more information to be able to calculate exactly. But when we're just doing basic integration, we have to follow this rule, and we basically do what we thought, and you hopefully work this out for yourself, because it's just the opposite. Okay, when we differentiate, we take one from the we multiply by the power and then take one away. If we're integrating, we do the opposite of that. We add 1 to the power, and then we divide by that new power. But because of that constant potentially being there, maybe not, we have to add on c for our integration. So that is your rule for integration. That is your formula. Okay. You notice this little symbol. So you'll either see this, and again, we have to be very, very careful when we're differentiating. We have to be careful with how we write it. We have to be careful with the notation. This is the symbol for integration, okay? And you'll see this. It's basically like an elongated F without a line in the middle, okay? But if you see this, it's basically asking you to integrate. But similar when we have the dy by dx, it's basically showing that we intend to integrate. So once we have actually integrated, then we don't write this symbol. So if you differentiate, you write y equals until such a point as you have differentiated, and then you start writing dy by dx equals. With integration, okay, if we have integrated something or if we intend to integrate something, we have to write this. And the dx is because we're integrating it with respect to x. So it's very similar to when we had the derivative. It was dy by dx, and that implied that we were differentiated y with respect to x. This is basically telling us, and the way this is written is telling us that we intend to integrate x to the power of n with respect to x. So that letter can change, but most commonly we're going to be using x. Okay, I'll go through that in more detail when we're doing some examples. But that's what it means, the integral of x to the power of n with respect to x. So don't say curly f thing without a line in the middle, x n dx. Okay, the integral of x to the power of n with respect to x. That's how you say that. Obviously, when we're writing it, we want to write it in the simplest form possible, which is this. Okay. Right. One thing to note is that when we're integrating, x to the power of -1 cannot be integrated in this way. Okay. If you think about it, it does make sense. Okay. So when we integrate that, if we add 1 to the power, we get 0. But then obviously when we divide by 0, you can't do it. It's undefined. So you'll cross that when you cross that bridge in advanced higher if you go on to do advanced higher, but basically you won't really see it very often. So if you get x to the power of -1, well, yeah, throughout higher you very rarely will have to integrate something like x to the power of -1. Okay, so it's not necessarily something you need to worry about until you get to advanced higher. Okay, so in general rules, if you remember when we differentiated and you had two things, for example, if you had x squared plus x cubed, you differentiated them separately, right? The same can be said for integration. So if you're integrating basically an addition of two separate functions, so for example, x squared plus x cubed with respect to x, you can integrate them both individually, okay? Likewise, okay, when we differentiated something in terms of x that was just a singular index, so 3x, all that happened was the x disappeared and we were just left with 3. So the reverse of that is if we integrate something that's just a constant, in other words, if we integrate 3, we basically multiply it by x. And if you think about that, that again makes sense. If you were integrating 3, that's basically 3x to the power of 0. Remember, x to the power of 0 is just 1. So if you integrate 3x to the power of 0, the power increases by 1, it becomes 3x to the power of 1 divided by 1, which just gives you 3x. Okay, same kind of applied, as I say, in reverse when we're differentiating. You just got to remember what it means when it comes to integration. And of course, you have to add the constant. Okay, right, let's do some examples. So it looks very, very similar, same kind of questions in terms of differentiation, okay, but we're just going the opposite way. And this is part of the battle. Okay, if you ask to integrate, it's the opposite of differentiation. You need to know the difference between the two. You need to be able to do each one individually and obviously correctly. Okay, so if we're integrating with respect to x, so we've got x to the power of 6. So we will write it like this, the curly f thing, x to the power of 6 dx. That's what we're doing. We are integrating x to the power of 6 with respect to x. Okay. And to do that, so we need to check again with differentiation, and there's a lot of similarities here, so don't don't get too confused, okay? Spend a lot of time doing this in terms of practice so that you know the difference between the two of them. But we have to write it in such a way, and what's going to happen further down the line, or in the next slide, I think, to be honest, is that you might get non-integratable form. So something that's not an integratable form in the first instance, you'd have to change it. It's exactly the same as differentiation. Okay, so the first thing you want to do when you're integrating is check that it's in integratable form. In other words, is it x to the power of something? Okay, these ones all are set up accordingly, but obviously when you see something like x to the power a quarter, x to the power -2, chances are in an exam, in a test situation, it wouldn't be written in that form, in which case you want to write it in this form first of all, okay? We're just focusing on the integration just now. So this is what we're doing, integrating x to the power 6 with respect to x. It's in integratable form, so we can just bash on. So we're going to add 1 to the power and then divide by that new power. X to the power 7 over 7. And that is almost it. We've just got to remember the plus c. Okay, so every time you're integrating, you're going to add on c just in case. Further down the line, as I say, we're going to work out what that c might be, but we don't have enough information at the moment, so we've got to assume that there could have been a constant, in which case the answer is x to the power 7 over 7 plus potentially some constant. and that's all we write. Okay. So for the second one, same idea. We are integrating x to the power of minus 2 with respect to x. Curly f thing, x to the power of minus 2 dx. That's what that means. Okay. It's in integratable form because it has an index, so we can just go ahead and integrate. 1 more than minus 2 is minus 1. We divide by minus 1, and we get x to the power of minus 1 over minus 1 plus c. Okay. Right, you can rewrite this obviously in a slightly neater form. X to the power of minus 1 divided by minus 1. If you divide by minus 1, it just becomes minus. X to the power of minus 1 is 1 over x, so it's just minus 1 over x plus c. Right, you have to write the plus c in every single line. Okay, it doesn't just suddenly disappear for this last line. So if you've got it there, it's here, it's still here, but that is our final answer. Okay. So if we're integrating x to the power of minus a quarter, or x to the power of a quarter, sorry, with respect to x, same idea, just be careful with your fractions. You're adding 1 to a quarter, and a quarter plus 1 is 5 quarters. So you end up with x to the power of 5 quarters divided by 5 quarters, and obviously you've got your plus c. Okay, right, this doesn't look very nice, so we want to write it in the best way possible. If you're dividing by 5 quarters, divided by a fraction, so you times by its inverse, you flip it upside down and times by it, so x to the power of 5 over 4 times by 4/5, and then add on a c. Best way of writing that is 4/5 times by the 4th root of x to the power of 5 plus c. So just the same as before, you're still dealing with your indices, you're still writing them in the most appropriate form, and then dealing obviously with your fractions, and just making sure that you add plus c at the end. Okay, so this last version, okay, we're integrating all of this, but the idea is we can integrate each one individually. Okay, so don't worry about the combination of them all. Just focus on each individual part as one. So integrate that, integrate that, integrate that, all with respect to x. Okay, but when you're writing this, it has to be in brackets. Otherwise, it kind of implies that it's just the 3 that's with respect to x. Okay, so put it all in brackets with respect to x. Right, so going through them each individually. We have x to the power of 4, so this becomes 1 greater, so it's x to the power of 4 divided by 4, and we've still got the quarter. So notice nothing happens to this quarter when we integrate. Okay, it's still there, and a lot of people just rewrite it and then just focus on the x to the power of 3 part. X to the power of minus a half, so 1 greater than minus a half is 1 positive half, okay, and then we divide by that half. And then we've got to be careful of this plus 3. So when we differentiate, it disappears, but when we integrate, it becomes 3x. Okay, so likewise, when we differentiate 3x, it became 3, but we're going the opposite way just now, so it becomes 3x. As I say, we've got to think of this. This is basically 3x to the power of 0. 1 more than 0 is 1, divided by 1, 3x to the power of 1 over 1, or just 3x. Okay, before you got used to the idea, if you differentiate 3x, you just get rid of the x. Now, when you've got something like 3 and you're integrating it, you just stick an x on. And then, of course, we've got our plus c. Okay. So throughout all these steps, don't forget the plus c. And then it's a case of just tidying it up a little bit, writing it in its neatest possible form. A quarter times by x to the power of 4 over 4 is a 16th of x to the power of 4. If we divide by a half, it's the same as times by 2. X to the power of a half is root x, so it's minus 2 root x plus 3x plus c. Okay, so lots going on there, but a lot of it is the same as what you're doing in differentiation. But obviously the main part, the actual integration side of things, is just the opposite of what you do in differentiation. But dealing with the surds and indices and all that kind of thing, that's just exactly the same as what you do in differentiation. Okay, right. The next slide, I think, is I hope it is at least, is dealing with when it's not in integratable form. Okay, so it's probably worth you going to practice in some of this and then come back and do the next part. Okay. So as I said, similar to differentiation, we can have to integrate something that is not already in integratable form. Okay, it's just exactly the same as I say as differentiation. We're still going to write it. Nothing changes in the first instance. It only changes when we actually integrate it. So something like this, the integral of 2 over 3x to the power of 5, we've just got to think about a bit more carefully. It's still times by 2, it's still divided by 3, so we can kind of take that out as a fraction, 2 over 3, and then the x to the power of 5 being on the bottom is the same as x to the power of minus 5. So this is what we're integrating 2 over 3 x to the power of minus 5 with respect to x. Okay, so the power increases by 1, minus 5 increased by 1 is minus 4, and then we divide it by minus 4. Again, note the fact that the constant bit, or the coefficient, sorry, 2/3, nothing changes with it, so you can kind of almost write it separately, deal with it afterwards. X to the power of minus 5 becomes x to the power of minus 4 divided by minus 4, and obviously you've got your plus c. And then simplify this down a little bit. Deal with the index part. X to the power of minus 4 becomes 1 over x to the power of 4. It's 2 over minus 12, or minus 2 over 12. X to the power of 4 plus c, which obviously can be simplified to minus 1 over 6x to the power 4 plus c. Okay. So for the next one, if we've got two parts, okay, deal with them individually, but obviously if they're surds, you can't integrate as is, just like when we're differentiating. So we want to write this in an index form first of all. So we are going to integrate 6x to the power of a half minus 5 times by x to the power of 3 over 2. Careful with that one. Okay, and we're integrating that with respect to x. I should really have brackets around that. And so when we integrate, increase the power by 1, it becomes 3 over 2 divided by 3 over 2. 5x to the power of 5 over 2 over 5 over 2. And obviously all we're doing here is we're dividing by a fraction. If you divide by a fraction, you're timesing by the inverse of that fraction. So just kind of deal with that separately, as I say. And notice the same again here. 6, nothing's happened to 6 yet, nothing's happened to 5 yet. We'll deal with it in a second. So you can literally just write them down. Okay, and obviously you've got your plus c. Okay. So we're timesing by 2 over 3 here, which becomes 12 over 3, x to the power of 3 over 2. We're timesing by 2 over 5 here, in which case it becomes 10 over 5. Both of these can be simplified. The indices can be written as surds, in which case it's 4, 12 divided by 3 is 4, square root of x to the power of 3 minus 2x to the power of 5 over 2 becomes the square root of x to the power of 5. Notice I've got plus c in every single line. Okay, so the final example there is very similar to when we had differentiation. When it's like this and we've got the x squared on the bottom, we want to separate it into two fractions and then integrate from there. So this becomes the integral of x to the power 4 over x squared minus 7 over x squared. So again, just remember this is the opposite of when we're adding and subtracting fractions, and we're doing it with respect to x. Simplify them first. X to the power 4 divided by x to the power of 2 is x to the power of 2. Remember the indices are just taken away, and it becomes 7x to the minus 2. And when we integrate, it becomes x to the power of 2 plus 1, which is 3, divided by 3. 1 on top of minus 2 is minus 1, divided by minus 1. And then we have x to the power of 3 over 3 plus 7 over x. So the minus 1 here, if we divide it by minus 1, it becomes, the whole thing becomes negative, but if we're taking that away, it becomes positive. X to the power of minus 1 is 1 over x, so it becomes 7 over x plus c. Okay? Yeah, I'll leave it there.